Welcome back. Today we're going to see the most popular numerical method for approximating a solution to the heat equation, which is the Crank-Nicolson method. If you recall from the previous videos, we had an explicit method where we could obtain the solution at a time step L plus 1 as an explicit formula of the field configuration at step L, and we had an implicit method that we obtained the solution at time step L plus 1 by solving a matrix equation, right? And we saw that the explicit method, while simpler and in some ways like easier to parallelize than solving a matrix equation, turned out to be unstable for large time steps, which did not happen with the implicit method. And then what's the Crank-Nicolson method? Well, it is simply an average of the forward time centered space scheme, which is the explicit one, and the backward time centered space scheme, which is the implicit one. So if we again have our heat equation, del u del t equals d del square u del x square, and now we will write the derivative. You see that we have a factor of 2 here to indicate an average. We will average the derivative at the L plus 1 time step and at the L time step, right? And we'll see that this method turns out to be it is also unconditionally stable, like the implicit one, but unlike the implicit one, it doesn't really overestimate high frequencies. It does a much better job at estimating the exact decay of the smaller frequencies. Alright, so as before, we define alpha equals d delta t divided by delta x square, and if we multiply by 2 and rearrange, we put the L plus 1 things at the left hand side and the L things at the right hand side, and then we have minus alpha uj minus 1 L plus 1 plus 2 1 plus alpha uj L plus 1 minus alpha uj plus 1 L plus 1 equals alpha uj minus 1 L plus 2 1 minus alpha uj L plus alpha uj plus 1 L. And again, this equation is valid for j ranging from 1 to n minus 1, and again we write it as a matrix equation. So see again that we have a 3-diagonal matrix. Just in the case of the implicit method, it's again very easy to solve, and the difference here is of course the values at the main diagonal are different in the implicit one, and also the solution, the independent terms here are different. You see that we have to do some sort of a convolution with like the sequence, just like in the explicit one. And again, if we solve this, we'll find the values at the step L plus 1, and yeah, that's it. And then now if we do the stability analysis just we had before, if you recall, at the explicit method, like this factor here was 2, right? And at the implicit one, this factor was 2 ak, but in the Crank-Nicolson method, it is 1 plus ak, like the average of these two. And then if we isolate ak, we see that the amplitude for the frequency will be ak equals 1 minus alpha 1 minus cosine k delta x divided by 1 plus alpha 1 minus cosine k delta x. And as before, the zero mode k equals 0 has the correct ak equals 1, and the dangerous Nyquist modes k delta x equals pi has ak equals 1 minus 2 alpha divided by 1 plus 2 alpha for every alpha. And just to show that it is indeed stable, we have 1 minus 2 alpha is less than 1 plus 2 alpha for every positive alpha, and then if we divide 1 plus 2 alpha in this inequality, we'll have ak less than 1. And to check that ak is greater than minus 1, again, since we have 1 plus 2 alpha larger than 0, we need to have 1 minus 2 alpha larger than minus 1 minus 2 alpha, which implies that 1 is larger than minus 1, which is always true. So we have both that ak is less than 1 and ak is greater than minus 1. So this method is unconditionally stable, just like the implicit one. And then what is the advantage of the Crank-Nicolson method with respect to the implicit one? Well, it happens if we expand this function here, right? I used the Wolfram alpha. You can use like any symbolic manipulation software you want, but if you expand this in a Taylor series, you have that ak equals 1 minus alpha k delta x squared plus alpha times 6 alpha plus 1 times k delta x to the 4th divided by 12 plus something of order k delta x to the 6th power, right? And the exact response, which we know from the first video, is just the exponential of minus alpha k delta x squared. And well, this Taylor expansion is simpler. It is just the Taylor series of an exponential. It is 1 minus alpha k delta x squared plus alpha squared divided by 2 k delta x to the 4th power plus O k delta x to the 6th power. And here we see that they are first order accurate, and then every approximation needs to be accurate for first order, or else it will not work. So the three methods, they are accurate to k delta x squared, right? But we see here that when alpha is large, for larger time steps, alpha squared divided by 2 is more or less the same as this one, because you can see that when alpha is very large, 6 alpha plus 1 is around 6 alpha, so we get 6 alpha squared divided by 12, which is alpha squared divided by 2, which means that for larger and larger time steps, the Crank-Nicolson method is accurate up to 4th order in k delta x, right? So it gives a better response. It does have a disadvantage compared to the implicit one, because we'll see that if alpha is very, very large, these large frequency modes, they have a k kind of close to minus 1, and that might be an issue in some applications, but it's usually not, right? So let me go to the code here, and just to show what's going on. So what I am going to plot the response for all of them, the exact, the explicit, the implicit, and the Crank-Nicolson method. So, and when we do this, now you can see, so this is the exact response, what we expect from the heat equation, right? And then we see that the explicit one is already diverges for this, right? Because it is, you can see it is gone below minus 1. As I mentioned in previous videos, the implicit one is always above the exact one, but the Crank-Nicolson method is different. It will be, if the time step is too small, it will be above the exact, but for larger time steps, it will be below. And you can see that it follows more closely the blue line here, so it is a better approximation for these lower frequencies, which is usually what you want. And the disadvantage, the thing that might stop you from using it, is that you see when it is a very, very high frequency, it is very close to minus 1 here. And we'll see the effect of this method in the numerical solution, that when you have a discontinuity or anything that causes some very, very high frequencies in the signal, you see that the Crank-Nicolson method does a very, very poor job if you take very few time steps of damping these very high frequencies. So if we go here, so Crank-Nicolson, and then just to go very quickly through the code, well, we have the usual stuff, which is our signal F. It is being sampled here, and then there's the exact solution using the FFT. And now for the Crank-Nicolson one, we set up the parameters. Here I divided in 10 time steps, and I divided space in n time steps, which is 100 in simulation. I set up alpha, and then here I have the main diagonal. This thing here, main diagonal, and now the lateral diagonal is here, which is these two. All right, and then I set up sparse matrix again to invert it, and then you see that's very interesting that in the explicit method we set a loop for m times y equals the convolution of y with something, and in the explicit one we said loop for m times y equals solve the linear system of something, and you keep updating y. But in the Crank-Nicolson method you do both things. You first do a convolution and then you solve the linear system, right? Very, very interesting. And then so if we run this code, so Crank-Nicolson, and look at this, here's the initial, the FFT, and the Crank-Nicolson one is pretty much a perfect match. But now, so for example, if I run like with one time step just to show this effect greater, see with one time step you see that if you run with one time step, the implicit one had some oscillations here, but they were usually like in a lower frequency, right? They would go around the whole signal. And the reason for that, of course, is because it was overestimating the high frequencies. But see that while even with one iteration, the Crank-Nicolson method is following pretty close the exact result, you see that when we have these jumps, which corresponds to high frequency, they appear as artifacts in the solution, right? And when you set m equals to 4, it already dampened them a little bit, but you see that there's this discontinuity here, which is pretty strong. This is still there, right? So, but when we run like 10 times, it is already gone. Like I said, depending on your application, you might decide that the implicit method is a better idea. But usually these higher frequencies, at least for image filtering applications, so these edges or these very high frequency things, we treat this with nonlinear terms in the equation, because, so for example, if you have the example of a denoising filter, or want to remove the noise, if you apply the standard heat equation, it would like destroy this edge, and we don't want it to do that. So what we usually do is we add some nonlinear terms to the equation to keep this edge, and this ends up somewhat cancelling the error in the Crank-Nicolson methods, and we only get the good results, right? But lower frequencies. Alright, I hope you guys enjoyed the beginning of this course. It was a lot of theory, a lot of interesting stuff, the heat equation, and the rest of the course will be a bit different. If you notice here, the content of a video depended on the previous one, but now it's going to be completely different. We're going to branch into several different subjects. All of them will like extend the solution that we have now in different directions. So for example, we want to solve the linear system with C++ code, or we will generalize to 2 dimensions. and then each video from now on will be independent, and then we will gather all the results at the end to implement an image filter. Well, that's it for now. I hope to see you guys in the next video, and bye bye.